Hello students, in this video we'll consider the integer power conformal maps. Let's consider the conformal mapping. W, we'll do a simple one, is z squared. It looks simple, but it actually gives us some really nice theory. Okay, that's a conformal mapping. Great. It's conformal everywhere except at z equals 0, right? This is conformal everywhere. But z equals 0. Because the derivative there is 2z at 0 that vanishes. So the derivative vanishes at 0, as we all know well, so it's not conformal at 0, right? In fact, it's doubling the angles. So think about that for a minute. It's really doubling the angles because the derivative is 2z, and so what's the effect on the argument? The effect on the argument is you're doubling the argument. So at that point where the derivative is 0, it's a doubling. So it's not exactly conformal, it's a doubling, okay? Excellent. And of course, let's write this in real imaginary parts. So clearly, W equals z squared is equal to x plus I. Y squared is x squared minus y squared plus I 2xy, real imaginary parts. So this is going to be u plus iv. U is going to be equal to x squared minus y squared, and then v is going to be 2xy. Okay? Now what I'm going to do is I'm going to try to understand how this mapping takes rectangles in the uv plane and rectangles in the xy plane and how it maps them, okay? All right, excellent. So let's look at the UV plane over here. So this is U, and then this is V, right? I'm gonna look at a rectangle. I'm gonna say that U is between C1 and C2, and V is between C3 and C4, okay? So we're gonna have this rectangle over here in the UV plane. How does this rectangle transform under this transformation over here? So in other words, which region over here did W equal z squared come from, right? So W, of course, is U plus IV, right? So I want to figure out the region this came from, so let's figure it out. So note that if U is equal to C1 and C2, so for these lines over here, okay? If U is between C1 and C2, C1 less than or equal to U less than or equal to C2, for example, what would that say? That would say that you're between what curves over here? You're between the curves x squared minus y squared is equal to C1, and x squared minus y squared is equal to C2, okay? So what do those curves look like? Those curves over here in the xy space, well, those curves are just hyperbolas, right? C1, x squared minus y squared is equal to C1, okay? And then over here, C2 is bigger, so C2 is going to look like this. Let's give us a little more space. Like that. Okay, so this curve is x squared minus y squared is equal to C2. This curve over here is x squared minus y squared is equal to C1. Okay, those are hyperbolas. And if I look at the other cross sections over here, let's look at these cross sections. These cross sections are for values of what? Those are for values of V between C1 and C2. So if V is between C3 and C4, between C3 and C4, so for V between C3 and C4, what curves do we have there? There we have 2xy is equal to C3 and 2xy is equal to C4, right? Okay. And so what do those guys look like? Those are also hyperbolas, so but they bend in the first quadrant over here like that, right? That is 2xy equals C3, and this is 2xy equals C4 like that. And so of course we know that the interiors get mapped to themselves. We get this region over here between these hyperbolas. So in other words, the region between two sets of hyperbolas, the region between these two hyperbolas maps onto the rectangle. Okay, Excellent. Let's do another example where I look at some other sort of rectangular shape in the xy plane and see where that gets mapped to in the UV space, okay? So this is very, very useful. Now, one thing I want to really highlight over here is that this is a standard problem from Calc 3. When you take a Calc 3 course, you see problems involving the change of variables theorem that involves regions like this. And the reason why that's important is because I can control the Jacobian of this thing, and I know it maps to a nice region in the UV space, right? And so I know that I can control the Jacobian because this comes from an analytic function. So we're going to really explore that connection because in some sense, analytic transformations are the absolute best type of transformations you can have. Why so? Because they're orthogonal curvilinear coordinates. In fact, you can see that these it's hard to see from this graph over here, but these graphs, the level sets, intersect at right angles to each other. So this is an orthogonal curvilinear coordinate system, which we've studied in differential geometry. Excellent. All right. So now let's look at this region. Can now consider the open infinite rectangle. I'll put rectangle in parentheses over here, right? Looks like this. Okay. Here's a point A, here's a point B, here's a point C, which is going to be the origin, and then here's a point D, okay? I'm going to call this value over here, let's call that value little b, okay? That's the x value, little b. So that's, of course, the real axis is over here. This is the real axis. This is the imaginary axis, right? And then this is my region in x and y, right? So this is like an xy. So that's my x-axis, that's my y-axis, right? And I want to figure out what this region gets mapped to in the complex plane. Okay, well, between a and b, let's parameterize this curve. Going from a to b, looks like what? Going from A to B, I'm really saying that x is B, so x is equal to B, and y is allowed to vary, right? So let's just let y be equal to y, right? So that's what that curve looks like. So y goes between, let's say, 0 and infinity, right? 0 less than or equal to y less than infinity, right? Good, so that's what the curve AB does. Where does that get mapped to? So let's look at our curve over here. So my x is equal to B, right? And my y is equal to y, right? So we have what curve? We have our u is equal to what? Is equal to b squared minus y squared. And our v is equal to what? Our v is equal to 2by. And so that says that y squared is really v squared over 4b squared. Okay? And I can plug that in and solve, right? So now I have what? Now I have u is equal to b squared minus v squared over 4b. And this, of course, is a parabola in the UV space. And so what does that parabola look like? Let's draw it over here. We'll fill in the rest of the details in a second. Here's u, and then here's v. That parabola looks like this. Okay? So in other words, here's a prime, here's b prime, okay? And then I want to see what's going to happen over here. So now, because for example, when v is equal to 0, where are you? So when your v is equal to 0, you're at this point u is equal to b squared. So that's going to be like the b squared over there, right? Good. All right. Excellent. Now what? Now, when we're going along this line from C to B, what's happening from B to C? From B to C, what are we gonna have over here? Well, now your x is equal to, your x is just equal to x between 0 and b, and then what's your y equal to? Your y is equal to 0 over here, right? So then in this case, what do you have? You have your u is equal to just this x squared, a real number, and then your v is equal to 0, right? So it goes from b all the way down to what? All the way down to 0, right? So in other words, from b to c, we go from b over here down to c prime over here like that. So you move along that direction over there. And then finally along D, what do we know? Along D, our u is equal to 0. So from C to D, our u is equal to 0, and our v is just equal to v itself, right? Y. And so in that case, what do you have? Then you have u is equal to negative y squared, and v is equal to 0. So this says that u is equal to negative y squared, and that's of course going where? That's giving you the whole negative x over here, right? So in other words, you're mapped into this sort of top branch of the area under the top branch of that parabola over there. So your point D prime is over here, right? So we have two sort of separate entities over here with this z squared map. You might say, wow, this was a very simple conformal map. Very simple, z squared, easy enough, right? We see from this there's a little bit of complexity in this, in the sense that the UV space, if I go from UV and I ask what points get mapped into a rectangle, it's the area between two sets of hyperbolas. And of course, these hyperbolas, the V hyperbolas, are what? Are 45-degree rotations of these other conic sections over here, right? So I can put them into each other by 45-degree rotations, right? And so that's one element of it. The other element of it is I have this interesting dynamic that happens on these open infinite rectangles over here. We've seen these in relationship to the conformal map sign. Very important. So these are very important regions in the complex plane, and they come to an area between the real axis and between an arc of a parabola, right? Very, very useful, right? Because I want to figure out ways of saying how do I invert this? We know inversion happens via the square root, but of course I need to take a branch cut for that to happen. So it's important to understand this example in this context going back and forth, so we can better understand the dynamics of the square root or then other roots of a polynomial. Thank you very much.